Hi, my name is Guokan Shang. The topic I'm going to talk about in this video is speaker change aware CRF for dialogue act classification. This is joint work with Antoine Tixier, Michalis Vazirgiannis, and Jean-Pierre Lorré. We are from the academic and industry sectors, École Polytechnique and Linagora in France, and Athens University of Economics and Business in Greece. A conversation can be seen as a sequence of utterances, as shown in this table. Dialogue act classification aims at assigning to each utterance a DA label to represent its communicative intention, including such as stating, questioning, and answering. DAs serve as helpful notations for a lot of downstream conversation processing tasks. Note that there are dependencies both at the utterance level and at the label level. For instance, given a single utterance here without providing any context utterances, it's hard to tell its DA among many possibilities, whether it's an agreement, a yes answer, or a back channel. On the other hand, we know that different labels have different transition probabilities to other labels. For example, a question is usually followed by an answer. There are mainly two approaches for DA classification. One treats the task as a multi-classification problem, in which consecutive DA labels are considered to be independent and are predicted in isolation. Another treats the task as a sequence labeling, or structured prediction problem, in which DA labels for all the utterances in the conversation are classified together. Recent work mainly uses two neuron architectures, by LSTM coupled with a softmax or CRF layer. Our work focuses on improving the latter, whose advantage is that it is able to capture the dependencies among consecutive utterances with BiLSTM and among consecutive DA labels with CRF. Based on our literature review, we found that the state-of-the-art models only take into account the two sequences, input utterance and target label, while the additional speaker input sequence is ignored. This finding motivated us to focus on and to address this limitation, since the speaker information could be helpful for dealing with this task. Indeed, research on term management has shown that dialogue participants do not start or stop speaking arbitrarily, but follow an underlying turn-talking system to occupy or release the speaker role. To give an example, we can say there is a change of speaker here. From A to B, this speaker change is not arbitrary. Speaker A asked a question to B, which is a turn allocation action performed to assign the next speakership to B. In this conversational situation, Speaker B has a right and is obliged to respond. This gives us evidence from the linguistic perspective that DA transitions should be conditioned both on utterance transitions and speaker transitions, which is a binary speaker change. Thus, a question is usually followed by an answer is more correct if the speaker changed. To address this limitation, we propose a simple modification of the CRF layer that takes speaker change into account. We evaluate our modified CRF layer within the BiLSTM CRF architecture. Our model consists of three layers. The first layer is a text encoder not shown on this figure, while each utterance xt is separately encoded by a LSTM layer with last pooling. Then we obtain a sequence of utterance embeddings UT. At the second layer, the sequence of UT is turned into a sequence of VT by LSTM. Let's call it conversation level utterance representation. Note that VT can already be used to predict locally the label through a dense layer with softmax activation, which results in the BiLSTM softmax architecture. However, this might lead to a non-optimal global solution if we consider the output label sequence as a whole. Instead, we use CRF that takes the sequence of VT as input and outputs the target label sequence Y. CRF is a general discriminative probabilistic graphics framework. Here, we focus on the neuron version of the linear chain CRF, in which the first-order Markov assumption is applied, so only neighboring labels are dependent. More precisely, it models a conditional probability Pyx, while Cxy is a feature function that assigns the path score to the label sequence y, giving the input sequence x. Then a softmax function is used to get the probability, while tilde y denotes one of all possible label sequences. The path score is calculated as the sum of emission scores or state scores h and transition scores g over all time steps. To compute the emission score, the conversation level utterance representation Vt is first converted into a vector of size k. K is the size of the label set. Then we take the element at index Yt, which denotes how confident the model in predicting the output label Yt at time step t. The transition score from label Yt to label Yt plus 1 is taken from a label transition matrix G of size k times k to be trained. A higher value indicates Yt is more likely to be followed by Yt plus 1. For example, in this figure, we have a conversation with 4 utterances and ground truth QASS labels. QAS stand for question, answer, and statement, respectively. Emission scores are assigned to the dashed top-down edges. Transition scores are assigned to the solid left-to-right edges, taken out of the transition matrix G shared across all time steps. The training objective consists in maximizing the sum of the scores associated with these edges in bold, corresponding to ground truth label sequence QASS, so that after applying the softmax function, the probability of this path is much higher than all other possible paths. And at test time, the optimal output label sequence is obtained with the Viterbi decoding algorithm. We extend the original CRF so that it considers as additional input the sequence of binary speaker changes Z. For example, the element Z23 equals to 0 means the speaker does not change from time t2 to t3. Specifically, instead of using only one matrix G as in the original CRF layer, we use 2 label transition matrices G0 and G1 to compute scores. G0 is applied to the speaker unchanged case, and G1 is for the speaker changed case. We experiment on the widely used switchboard dialog act dataset with 42 DA labels. The frequency of the 10 most represented DA labels is illustrated in this figure. Results in terms of classification accuracy averaged over 10 runs show that our model A by LSTM coupled with our modified CRF layer that takes speaker change as extra input outperforms the baseline model B by LSTM with the vanilla CRF layer by 1%. This boost is greater than the gains reported by previous attempts at leveraging speaker information. And to interpret the results in more detail, we show the confusion matrices for the 10 most frequent labels, representing close to 91% of all annotations. By looking at the diagonals, we can see that our model A on the left better predicts on pair with the baseline model B on the right, 7 labels out of 10, with absolute accuracy gains of up to 5.9 for the label SV, statement opinion. However, it decreases performance for the most frequent label SD, statement non-opinion. This can be interpreted as a consequence of the trade-off between SD and SV, since the distinction between them was very hard to make, even by annotators. We can observe that As opposite to the base model, our model has lower SD, higher SV recall values, and has higher SD, lower SV precision values. Nevertheless, our model is better for both labels in terms of F1 score. In addition to the 10 most frequent labels, confusion matrices for the 10 best and worst predicted labels by our model show that our CRF is most useful for the difficult and rare DAs requiring speaker change awareness. To check if our approach is more effective than other possible ways of incorporating speaker information. Similar to the base model B, we trained models B1 and B2 respectively concatenate the one-hot encoded speaker identifier vector SI and the speaker change vector SC with the utterance embedding UT. Results show that while they bring improvement compared to model B, they are not able to yield as big of a gain as our model A. Then we repeated these experiments with our model. Results of model A1 and A2 show that taking speaker information into account twice at both levels is not useful. We report the results of models C, C1, and C2 using the BiLSTM softmax architecture. We found that it is competitive with the BiLSTM with vanilla CRF layer. To sum up, these results indicate that our way of taking speaker information into account at the CRF level is the most effective. In the end, we tried to combine model A and B. Results show that the ensembling approach reaches new best performance as expected, but not the jointly trained model, in which we have 3 transition matrices, G basis as in the original CRF applied at each time step, and G0 and G1 as in our modified CRF. We illustrate in this figure the transition matrices G0 and G1 of our CRF layer. On the left and right, we can observe that overall they are not identical, which means that different transition patterns are learned for 2 cases. The dark diagonal of G0 shows that when the speaker does not change, most labels tend to carry over to the next utterance. On the opposite, G1 shows that changing speakers very often induce a change in DA. For example, yes-no question, the QY label, tend to transfer to NY, NN, and NO, yes, no, and other answers if the speaker changed, and to another type of question, QRR, all closed questions starting with the word all if the speaker did not change. This corresponds to the case where a given speaker elaborates on his or her original question. We illustrate the single transition matrix G of the vanilla CRF layer. We can observe that it tries to capture at the same time the patterns of both cases. For example, SV equally tend to transfer to SV, AA, and AR, while the transition towards SV is only probable if the speaker stays the same, and towards AA and AR if the speaker changes. Well, that brings us to the end of my presentation. We focused on demonstrating that taking speaker information into consideration was beneficial to the task of DA classification. We proposed a modified CRF layer that takes as extra input the sequence of speaker changes. Experiments show that our CRF layer outperforms vanilla CRF. Moreover, visualizations confirmed that complex speaker change-aware DA transition patterns can be learned in an end-to-end way. Future research should be devoted to address the limitation of the Markov property of CRF layer by developing a model that is capable of capturing longer-range dependencies within and among the 3 sequences, that of speakers, utterances, and DA labels. This work was supported by the Lin2 Meeting Assistant project, and thank you for your attention.